All right, so for the last lecture, we're looking at modes of speciation. So how do we get new species? And if you look on here, we have two words that I need you to know. One is allopatric and the other is sympatric. So allopatric means that there is some physical barrier between the two. So you can see up on the top of the trees, you have all the dark green trees, and then all of a sudden a river makes a canyon. So now there is no crossing and breeding, and eventually they become two separate species. That would be called allopatric speciation. So you want to key in on allopatric, you want to key into the fact there's some physical barrier. On the right, sympatric means it happens all together, that they actually have the ability to interbreed, but for some reason a population is introduced to a slightly different habitat and or condition, and they become a separate species on their own, and that's called sympatric, and we'll give you some ways that can happen. So we'll go through and look, and so allopatric speciation, what you're looking at is actually some ground squirrels, antelope ground squirrels, and again, the bottom picture is of the Grand Canyon. There's a north rim and a south rim. If you've been to the Grand Canyon, my guess is you've been to the south rim. That is the tourist attraction area. On the other side is where the long-term camping is. And there is a difference in altitude. Actually, the north rim is actually a bit higher. And so although they both have antelope ground squirrels, they are two separate species now because they don't breed. And there is this big, we call it the Colorado River and the Grand Canyon that keeps them apart. So that would be an example. For sympatric, there are two different types I want you to know. Polyploidy is having more, poly means many, haploid and diploid. We talked about, one set or two sets of chromosomes. Autopolyploidy is where you actually have a species that doubles its chromosomes. There's a mistake, non-disjunction, something like that. And then all of a sudden you have an individual with 6, and then all of a sudden you get the zygote with 12. And so because they're not reduced, you end up with this organism that may survive that has 12 chromosomes. So now you have a new species. You have your original species with 6, and then you have your tetraploid, which might be able to reproduce with another tetraploid. It may be possible. And so again, this doesn't necessarily happen in animals, higher animals anyway, because we don't deal with extra chromosomes well. But this definitely could happen in plants and some of the lower organisms. Another example of this is allopolyploidy. Just to let you know, autopolyploidy, just to give you an example, what they sell as a Boston fern, that plant in the house is actually, because of this, there is actually even a frog, gray frog is kind of the common name, although that one doesn't hold up. It's got several different names. But there's a frog that actually does this. So there are species that do it, for examples. Allopolyploidy, on the other hand, if you think of alloy, like in metals, that's a mixture. So this is where you have a species A, a species B, and there's some mistakes and things happen. And then there's a hybrid, and all of a sudden you end up with species A, species B, and now we even have species C. That's a viable fertile hybrid, which has added the two species numbers together. And so an example of this would actually be wheat for wheat bread. We have artificially done that, but the wheat for wheat bread is actually two different wheat species and a grass species that has been kind of blended together over time through artificial selection to get us wheat bread. So that would be an example of allopolyploidy. All right, and then let's talk about the bigger picture. Everything I've talked about up to this point has been really microevolution. We've looked at a single species making changes in a single species, and then even maybe coming up with another species that looks a lot like the species before. Macro evolution is really kind of looking at more, how do we get from one level to another? So we're not talking about, oh, we have another butterfly species, although that's the example they give you here. How does a reptile or a dinosaur evolve into a bird? That's more macro evolution. And I will tell you, you'll hear, oh, biologists argue that evolution doesn't happen. I don't think that's true. I think most, if not all, I mean, you always find a few biologists believe in microevolution. The macroevolution is the harder one to explain, and the one that has more issues. So what I want to do is just introduce this idea to you. We talk about this more in our biology 2 class, but macroevolution, there's really 2 types: gradualism and punctuated equilibrium. Gradualism is just like it sounds, is slowly over time. You have 2 species that kind of morph into 2 separate ones. And this is just generation after generation, and typically due to 2 different habitats. Punctuated equilibrium model, on the other hand, is a little bit different, where you have long periods of time where the species don't change all that much. And then all of a sudden, over a short geological time, there's a massive change, creating a new species. And that's called punctuated equilibrium. So think about what the name means. Equilibrium means the same. So over long periods of time, very little change. Punctuated, it means you break it up. And so we have 2. This is Ernst Mayr. He's the one I talked about way back when we were talking about the origin of species. He's the one that came up with the idea. Now, this is one of his later pictures. Actually, it's a better picture. A lot of them, he looks like he's drunk. This one, he looked a little funky. But gradualism is also called neo-Darwinism. It's really taken Darwin's idea and just adding time to it, that small changes over time can cause drastic changes. And that would be the supporter. The other ones, Niles Eldredge and Stephen Jay Gould, both evolutionists. Niles Eldredge is I think he's still the curator of the National Museum for Vertebrates. I believe that's his job title still, but could be wrong. And then Stephen Jay Gould actually was a professor. Unfortunately, he died of cancer probably 6-7 years ago now, I think. But he's written a lot of popular books on evolution. And so these guys were looking at the fossil record and changes in animals over time. And what they found out is they didn't see the fossil record look like gradualism. It looked like when you're digging the rocks, you see things look kind of the same for a long period of time. And then there's an extinction event or some kind of major change, and boom, all of a sudden all the organisms look different again. And so this is where they came up with the idea of punctuated equilibrium. I am going to guess, in this big controversy of which one, I'm telling you, I'm guessing both, depending on the species. Some did it by gradualism, others by punctuated equilibrium. So it's major war, and I think they're both right. And with that, we will stop the share and stop the recording.